All right, we're going to take a look at the crisis that we're having around the world with COVID-19. And let's take a look at this. Let's try to figure out, is this a linear relationship in terms of the number of cases growing? We're going to take a look just in Tokyo here. Or is it growing exponentially? And maybe that changes over time. But let's just take a look at a particular time period and see if we can figure this out a little bit. So on March 20th, we knew that there were 58 known cases of people testing positive for COVID-19 in the Tokyo prefecture. By March 23rd, there were 98. So that's actually, it's gone up in 3 days from March 20 to March 23rd. We went up by 58 to 98. That's by 40 cases. So 40 cases in 3 days. How do I find what the average number of new cases per day would be? Well, I take the 40 cases, divide them by the 3 days, and I'm going to get 13 and a third cases per day. If the virus continued to grow in a similar linear fashion, how many total cases would there have been on April 5th, which is 16 days after March the 20th? Let's go ahead and finish the table to find the answer. In each one of these cases, we're adding 13 and a third every day. So we take 58, add 13 and a third, you get 71 approximately. Keep your answer in your calculator and just add 13.3 repeating. And add them up as we go, and go ahead and finish the table. When you get to this one, you can put your answer into here. Okay, so having a linear growth by 13 and a third new cases every day. By the time we get to the 16th day on March 20th, we are going to have 271 total cases in Tokyo. And we will see later on. Let's see if does that pattern continue in this linear fashion. We will see. In the last two questions, you are adding the same number of cases every day since it was linear. But is that what really happened? What if we looked at this another way? Instead of asking what number are we adding to the total every day, what if we instead asked what number are we multiplying the total by every day? Let's just say you take the 58 cases we started with on March 20th, and we multiplied by this number here, 1.2 every day. If we multiply by 1, the number would stay the same. So the fact that we're multiplying by 1 and 2/10 every day means that it should be growing. And let's see what happens. So we're gonna do this from the March 20th to March 23rd. So we're gonna multiply by 1 and 2/10 3 times. Would we get close to that 98 cases? Try it out and see. When I multiplied by 1 and 2/10 3 times, I ended up with 102/10. Rounded that to about 100 total cases. And that is pretty close to 98. So yes, if by multiplying by 1 and 2/10 every day, we actually get pretty close to that same number of 98 that we had here, the actual number that we had back in here. We're off by a little bit here, but we're pretty close with 100 total cases. Okay, so if the virus continued to grow in a similar fashion, how many total cases would there have been on April 5th, which is 16 days after March 20th? We're going to have to fill in this table. We're going to have to take each one of these, multiply by 1 and 2/10, multiply by 1 and 2/10, multiply by 1 and 2/10. I'm curious if anyone back here realized that they're multiplying by 1 and 2/10 3 times, multiplied by 1 and 2/10 to the third power. If you using that idea, you could actually go through this table a little bit quicker. So go ahead and fill in that table and then answer the question up here at the end. So I got 1,072 total cases by March 20th, which is really interesting because if I compare that to the linear model that I had back here, I had 271 total cases. When I'm instead of adding the same number, if I multiply by the same number every time, I get a much bigger number, 1,072 total cases. So what's going to be the reality in this? Let's go take a look at the two graphs of these models here. Okay, and if I look here, we have two equations that we have. This one is the linear one. We start off with 58, so there's our y-intercept, and we're adding 13 and a third new cases every day, where x is the number of days. and that will give us a linear model. And it starts right here, actually at the point 058. And they should be pretty close to each other 3 days later. This one's slightly off here. It's a little bit less than 3 days where they hit here, but pretty close to 3 days later, they also are at the same point, because we were just looking at 2 points, one on a linear equation and the other one on an exponential one. So we're looking at an exponential equation. Now this one starts off with the number 58, and it multiplies it by 1 2/10. And it starts off multiplying by 1 2/10 one time, then it multiplies by 1 2/10 two times, and then it multiplies by 1 2/10 three times. But basically, we're multiplying it by 1 2/10 x times, which is why we use the x in the exponent here. Really interesting that we created that. This is actually called an exponential function, and it's called exponential because the variable is in the exponent. Keep in mind that we've already done a quadratic where we had exponents like y equals x squared, but the number was the exponent. In this case, the variable itself is the exponent. That makes it an exponential function. So here's what this one looks like. You guys have already seen the shape of an exponential function. It's going to start off slowly, and then it starts to shoot up, and it curves and gets steeper and steeper as it goes up. So there's an exponential function. Now the question is, which of these models, the linear one or the exponential one, actually models the real situation that we had in Tokyo? I actually put in the data in here. This is starting on the same day. Day 0 here was March 20th. By the time I get to the 16th day, we're on, April 5th that we are going to. And then we have, let's take a look at these data points here. Well, here are the data points. It is pretty obvious which of these models fit this situation better. Certainly looks like the exponential function is a much better model. This did not, the number of COVID cases did not stay constant, growing by the same number every time, adding the same number. It is much better. It was actually multiplying by the same number, 1 2/10, pretty close to multiplying by 1 2/10 all the way through. It looks like it actually was faster here, and then it slowed down and then speeded up here. And that one, so it wasn't quite consistent in here. Of course, the way we're measuring in Tokyo might not be the most accurate as well. Maybe it was growing. We know that there's probably not fewer than these unless we had some false positives, but it is likely that there was actually more of them, and it might have been even growing faster than this. We don't know. If we take a look, I want to see these equations again. Notice again, we're multiplying by 1 2/10 every day. I just want to, this is sort of a preview of where we're heading in this. This number here that we have in front, this is what we usually consider the letter A, is the number that we start with. And then the letter B, which is our base, is the number that we multiply by X times. A little bit about this base, though. This is really interesting. If you multiplied by 1 each time, it would not have changed at all. Multiply by 1, by 1, by 1, by 1, nothing ever changes. That's when everything keeps its value. In other words, it keeps 100% of its number. So the number 1, if we put it in there, would keep it at 100% of its value, and there would be no increase whatsoever. But if I add, in this case, 2/10 to that 100%, I'm actually adding 20% more. So this is actually a curve, an exponential curve, that is growing by 20% every day. And actually, that's a pretty close model to what actually happened in Tokyo during this time. The number of cases was actually growing pretty close to 20% a day between those dates. All right, we've pretty much already answered the rest of the questions on here. So see if you can go through, just go and answer questions 7 through 14, and then check your answers with mine. All right, so here's the linear equation we got. Here's the exponential graph that we got equation. Why is the equation for the exponential graph called exponential? Well, one of the variables is an exponent. It's really important to understand that just because it has an exponent does not make it exponential. The variable has to be in the exponent for it to be exponential. Okay, Then we went and took a look at the table, and we saw that those points matched up really nicely with the exponential curve. And so definitely the exponential model, the multiply by 1.2 model was a much better predictor of that. What kind of growth was that? That was exponential growth. What happens mathematically to make that kind of growth? Well, we multiply by the same number over and over again. We were multiply by 1 and 2/10, multiply by 1 and 2/10. What's a shortcut way of multiplying by that same number over and over again? Using exponents. All right. Can you see why the relationship of multiplying by the same number over and over will result in an exponential function? I really hope that you can see that now.